probably get started. So last week, just a brief recap of what we saw. We had automorphy lifting theorems. In two cases, we had one in the ordinary case and one in the Fontaine-Lafay case. And for the rest of today, we'll just need this one. And I'll just remind you that this required that both R and the automorphic lift R pi both be ordinary above L. And it had no sort of connects or strongly connects condition away from L. And then we also had potential automorphy theorems that Richard explained. And I just remind you that these were providing, after base change, ordinary automorphic lifts. And today, I want to state improvements to these results. So the first result, theorem 1, will be an automorphy lifting theorem. So we're going to have f over f plus Cm extension. Mu is going to be a character of gf plus and continuous Theorem. And R is going to be our Galois representation. Continuous. And what we're going to impose some conditions on R and then deduce that it's automorphic. So the first condition is that it's conjugate self-dual. So this, again, this could be sort of, in the last time I spoke, I was sort of always talking about representations into this group Gn, because I wanted to explain how the R equals T theorems were going to work, and this used deformation theory for this group. But for today, I'm going to switch back to using GLN. Secondly, assume that R is unramified almost everywhere. So these two conditions are essentially necessary because, well, the second one is, and the first one is because we so far only know how to associate Galois representations to conjugate self-dual automorphic representations. Third condition is the following. So for all primes v dividing L, the restriction of R to the decomposition group of V is potentially diagonalizable with distinct Hodge-Tate numbers. So this condition was introduced 2 weeks ago. Let me just remind you what it means. It means that there exists K over Fv, a finite extension, such that R restricted to Gk is crystalline, and R restricted to Gk connects to some diagonal lift. And connects meant these two representations lie on the same irreducible component of a crystalline lifting ring with fixed Hodge-Tate weights. For, we're going to need some conditions on the image of R bar. So R bar restricted to GF zeta L is irreducible, and L is bigger than 2 times n plus 1, and zeta L is not an element of F. And then the last condition, right over here, 5, is that there exists a polarized regular algebraic cuspidal automorphic representation pi chi such that, well, first of all, the Galois representation associated to pi will be congruent to R mod L. So I want to say R bar and the characters, the multiplier characters we get are also congruent mod L. So I want to say R bar mu is equivalent to RL pi RL chi epsilon to the 1 minus n. So implicitly I've just fixed some isomorphism between QL bar and C to allow us to define these Galois representations, but I won't include it in the notation. And secondly, so essentially the same condition that we had for R on point 3, we want to assume here for R pi. So RL of pi restricted to GFV is potentially diagonalizable. And pi v is potentially crystalline. Potentially unramified. At all v dividing L. And then the conclusion is that R is automorphic. And in fact, it's automorphic of level prime to L, of level potentially prime to L.
There's something wrong in the condition 1. Presumably it's the central character of the second. You don't mean that mu bar is like is RL of chi bar? What does that mean? So it's chi. Okay, I'm sorry. Okay.
Yeah.
Yeah. All right.
Do you assume that the weight of the automorphic form could be the same as of the?
No. So there's the weights. There's nothing assumed about the weights.
Oh. But it's a diagonalizing condition, then they have to lie in the component the same way anyway.
So I thought Tong was asking about the Hodge-Tate weights of this representation and this representation.
So you don't worry about Sarah conjectures the weight? The weight, you don't worry about that? Okay.
I mean, we're allowing these things to be sort of ramified in different ways. If that's what you're worrying about, they're both potentially crystalline. And Bao, I think these points these representations have the same Hodge-Tate weights, but this is just some auxiliary. Maybe many choices for this diagonal.
Sorry, can you
It means
Maybe you
that
said it, but
it means that I probably didn't say it actually. So this R will be the Galois representation for some pi prime, and it means that after a finite extension, pi prime becomes unramified above L.
okay.
Which you would expect because R is potentially crystalline. Leave that there. So remarks. So this generalizes the results. The lifting theorems from last time. Except I'll say at least, well, once we restrict to potentially crystalline R, in the ordinary case. So why is that true? So why? Well, basically, the Fontaine-Lafay condition and the condition of being ordinary and potentially crystalline, both of these imply potential diagonalizability. And secondly, I just want to remark, so we don't assume R and RL pi have the same Hodge-Tate weights, as Tong asked. And thirdly, we don't have sort of strongly connects or connects condition at the primes away from L. And then essentially as a corollary of this result and the potential automorphy theorem stated last time, we get the following result. So under assumptions 1 to 4 only, so if we just take this Galois representation and make the first 4 assumptions, but don't assume that the residual representation has an automorphic lift, then we can make the following conclusions. There exists f prime over f plus CM Galois extension such that R restricted to GF prime is automorphic. So we get a potential automorphy result for R. Yeah, so, and then sort of so last week Richard added a bunch of remarks after each of the 2 theorems he stated, and they all apply here. So we can be disjoint from any fixed extension of f, can insist that we're Galois over some sub-extension over which f is Galois, and we can do this simultaneously for more than one representation R valued in L primatic fields for different L prime, and so on. So let me try here, and I'll just give the proof of this, assuming theorem 1. Mhm.
There's no condition on the object waves.
Well, they're distinct.
Oh, they are distinct. It's three.
Yeah. So what's the proof of this? Well, from I think it was theorem B of last time. Well, there exists f prime over f as in the statement. Well, Cm Galois and a pi chi, so polarized regular algebraic cuspidal automorphic representation, and this will exist over f prime such that so r bar restricted to gf prime will be isomorphic to RL pi prime. Let me go over here. Secondly, mu restricted to the underlying totally real field of f plus will be RL of chi cyclotomic to the 1 minus n. We can also assume that the image of R doesn't change after we make this base change. So I can say the image of R of G of f prime adjoins zeta L equals the image of R value R bar of G of f zeta L. So this ensures that this ensures that condition 4 will remain true after the base change. And zeta L not in f prime. And pi is ordinary and unramified above L. And then we see that we've satisfied everything. So then we can apply theorem 1 over f plus. And we get the R restricted G of f plus is automorphic. Okay, so for the rest of the talk, I want to try and describe the idea of the proof of theorem 1. Oh, I did want to say also that, I'll write it over here, can weaken the condition in both in point 4 that L is bigger than 2n plus 1 to L being bigger than 2 times d plus 1, where d is the maximal dimension of an irreducible subrepresentation of R bar restricted to, let me just say here, the subgroup of GF generated by all CLO pro L subgroups. I think it's a slightly weaker condition and guarantees any adequateness properties we'll need when we go through the proof of the theorem. Okay, so the idea of the proof is to use, so first of all, a tensor product trick of Michael Harris. And secondly, the minimal automorphy lifting theorem in n squared dimension in dimension n squared. So 2 weeks ago, I described minimal automorphy lifting theorems, and these were where we assumed that R and R pi were on the same component at all places. So at all places above L and at all places away from L. And so what's the basic idea then? So, well, to explain A, so what is this tensor product trick? So first of all, let me say that without loss of generality, we may assume that R and RL of pi are crystalline above L. We're assuming they're potentially crystalline, so we, by the solvable base change result of Arthur, Closel, and Harris, we can just make a base change to make everything crystalline. So we can assume they're crystalline and diagonalizable. So let's say that for V dividing L, let's say we just pick some V dividing L, and we look at R restricted to the decomposition group of V. Well, this is diagonalizable, so it connects to some that lives in the same component as some diagonal representation. And we have something similar for RL of pi. We get some other collection of characters. So each of these will be, these are all crystalline characters. Excuse me.
So the sides here are connected, right?
Yes, they're little tildes. So now the idea is to choose a cyclic CM extension M over F of degree n and characters, continuous characters, theta and theta prime from GM to QL bar. And we want to choose these characters to be crystalline above L and with the following property. So first of all, so if they're crystalline above L, we want them to be equal to each other residually. So these are the corresponding residual characters. So theta and theta prime actually take values in ZL bar cross, and we can reduce mod L. And we want to get the same result for each of them. And then the third thing we want is that, so let's first of all take theta, and then I can induce from GM to GF, and this is going to give me an n-dimensional representation of GF. And the condition I want is that when I restrict this to GFV, I'm now going to get some crystalline representation. And what I want to get is something that connects to RL of pi. Or equivalently, since connects is an equivalence relation in the crystalline case, equivalently it connects to this diagonal representation chi1 prime plus chi-n prime. Okay, and the other condition we want is the obviously the sort of opposite of this. So we want that when I do when I induce theta prime, I want to get something that connects to R restricted to GFV. So how'd you go about doing this? But it's I think it's automatic for a continuous character. So how can we arrange this? So we choose, well, first of all, choose M to split completely above V. So let's say the primes, let's say V splits as W1 up to Wn in M. And then this guarantees, well, this implies that when I look at this induction and restrict to GFV, I'm going to get something diagonal. It's just going to be the sum from I equals 1 to n of theta restricted to GMWI. And now I want to actually get something that connects to this fixed, this chi1 prime plus chi n, all the way up to chi n prime. So now, well, also choose theta such that the Hodge-Tate weight, so Hodge-Tate weight of theta restricted to the decomposition group at Wi at some embedding tau is equal to the Hodge-Tate weight of chi prime I with respect to tau for all tau, let's say embedding MWI into QL bar. So this is something that you can do. You can, when you want constructing a character of a CM field, you're allowed to choose the Hodge-Tate weights as essentially half of the places above L. So you have the freedom to actually to do this. And now once you've done this, you're in good shape. So then this implies that theta restricted to GM WI is an unramified twist or just of chi I prime restricted to GM WI. Well, probably should have said it just means these two characters differ by an unramified character. And now, so we want to show they connect. So, well, first of all, we have to show that they're residually the same thing. So make a base change to ensure that we can always just assume they're trivial residually. At these particular places. So now we have that they're actually deformations of the same thing, and to show they connect, it's very easy. We can just deform by unramified characters to get that they connect. So
Where is your first line true before base change? You are just fixing the odd state weights.
so yeah, so if you...
Are saying it is on an unramified twist, or maybe after some final?
No, it is on the nose, because for a crystalline character...
So maybe you didn't say everything is crystalline. Choose theta is crystalline.
Yeah, I think that was the first
Oh, it's in the
up here. So I just wanted to, just make sure everything is crystalline, and then once you fix the Hodge Tate weights, you fix exactly the inertial. And then it's, again, if you have two characters that differ by something unramified, and it's very easy to show that they connect, because you just change what's happening on one particular choice of Frobenius lift. Okay, so now suppose we've chosen these characters theta and theta prime so that they satisfy these conditions here. And then the point is, so the point is of choosing these things was that when we look at our tensor with the induction of theta and RL of pi tensor with the induction of theta prime, we've now established that if I restrict this to this decomposition group GFV, this is the sort of this guy here that divides L, then these representations connect to each other. Essentially because we chose theta so that these two connect, and we chose theta prime so that these two connect. And now, so we have this, and now also that this representation on the right-hand side is automorphic. Because we can rewrite it as the induction from GM to GF of RL pi restricted to GM twisted by theta prime. And this is true because we have automorphic induction. So now this n squared dimensional representation connects, so its residual representation has an automorphic lift, and moreover, this one connects to the automorphic lift at all places dividing L. So we're starting to look like we might be able to think about applying a minimal automorphy lifting theorem. Actually, maybe I should go up here. So this suggests the following. First, try and prove that our tensor in theta is automorphic using a minimal lifting theorem. And then secondly, having done that, we want to deduce that R is automorphic.
I'm sorry, just a question about this. But I don't find it anywhere. At some point, you have to assume that your inducing character is very regular because so you have gaps in the Hodge tensor product.
I'm getting to that.
Sorry.
Yeah.
So far, this is correct. Okay. Yes, you are just saying.
I mean, they have the same Hodge-Tate weights as
Yeah. Okay.
the things we started with. So we've got two things we need to do, and this second step that we know how to do. We know how to deduce R is automorphic if we know this is automorphic, and this is an argument of Harris, maybe Harris and Taylor, I think. I'm not quite sure.
This setting is in a paper of which you're also.
But I think the ultimate argument. Bootstrap. So there's a couple of stumbling blocks with So the first problem, which Laurent Clausel just mentioned, is that we could run into problems with the Hodge-Tate weights. So there's nothing at the moment guarantees that when I form this induction, that so let me just say this way, that this tensor product may have repeated Hodge-Tate weights. And once we're in that situation, then none of the methods that we talked about in previous weeks apply. And then the second issue is that the minimal automorphy lifting theorem requires that we have a sort of R connects to RL of, it's supposed to be a capital pi, for all v not dividing L. So the minimal theorem required that not alone are we on the same component at L, but also at all of essentially this just boils down to at all ramified places, the two lifts we have to live on the same component. And we haven't said anything about that yet. So where are we? I think I need to go here. So ultimately, what we get from this idea is the following theorem, which I'll call Theorem 3. And this is it's a weaker version of Theorem 1. And what it says is, so let's suppose we're in the situation of Theorem 1. And let's suppose in addition that, first of all, so we're going to just rule out this possibility that we have repeated Hodge-Tate weights. So we just assume that R tensor RL of pi has distinct Hodge-Tate weights. So remember, the induction of theta has the same Hodge-Tate weights as RL of pi. And let's also assume that R restricted to GFV connects to RL pi restricted to GFV for all primes not dividing L. Okay, so either what this will mean is that either they're both unramified, or they're both ramified and they live on the. Is that correct? Maybe that's not strictly. So strongly connects will be implied by this because of Anna's local global compatibility. So these local global compatibility implies these guys are always smooth points, so they can only ever lie on a unique component. So this will imply that we have strongly connects in this direction. So let me say, so just to be clear, let me say that this at all v dividing at all v not dividing L, where one of these lifts is ramified. So we assume either they're both unramified or we have this. Then R is automorphic. Pardon? Yeah, so I should say, so you choose M. M is chosen so that you still have, so you essentially still have this property holding. So you have to, you don't want to destroy the big image properties by your choice of M. By tensoring with theta, yeah. So and you choose theta as well. So you make a choice of M and theta to guarantee. Pardon?
Almost goes without saying, choose theta so that this thing is irreducible.
So in particular, this will have to be residually irreducible. Yeah. So just a remark. This is my next remark. Choose M. We choose M theta prime, so adequateness is preserved.
Sorry, maybe I mean, to go back to Shepard's point, I mean, you do need to do a little bit of work to ensure this thing is irreducible. We choose an auxiliary prime Q and
Yes.
ensure that theta's
Verify
ramified
that.
exactly one place above Q.
Yeah, I mean, there's an extra condition built into the choice of theta that will guarantee irreducibility of the induction. I didn't want to go into the details of it, but it's not completely. You have to make some argument to guarantee that you get what you want.
So it's part of the construction that the tensor product representation is irreducible.
Yes.
Yeah.
Adequate residual. Well, adequate because of the dimension.
Because we have a nice characterization of what we need. I kind of lost track adequateness.
Even residue.
So does the prime also become larger as it becomes bigger?
Um,
Dimensional column. Become 2 times that's 5%.
D is the same.
The image of the induction of theta has. Oh, the content of D is.
yes, n will have n won't be divisible by L, so this induction, as Jack said, will have order prime to L. So we choose. So okay, so we've addressed this, and now, so just a remark on. So to apply this minimal lifting theorem, we have to show that R tensor in theta connects to RL pi tensor in theta prime, or how to arrange that, I should say, at ramified place at V not dividing L. Well, essentially we sort of make things, so again what we're going to do is, again we're going to choose M to split completely above bad places V. Okay, and then in theta again is going to look something like this. Restricted to GFV again is going to be just a sum of characters. I give them the same name. I hope that won't cause too much confusion. And now these characters are just going to essentially, after a base change, these become unramified. So what we have is we're going to have R tensored with just a direct sum of n unramified characters. And that's looking very close to just n copies of R. So because we have this, so we have R looks close to RL of pi. Essentially, when we do the tensor product, we have something that looks very close to n copies of R on one side, and something that looks close to n copies of RL pi on the other side. And it's easy to show then that they connect to each other. Okay. So now we have this sort of now we have this weaker version of theorem 1, and now what we want to do is sort of get the full theorem 1. Okay, so let's so return to theorem 1. And now what we're going to do, our goal is to construct ordinary lifts R prime and R double prime of R such that, so let me try, well, I'll draw it as a picture first and then say exactly what I want. So we start off with this representation R that we want to show as automorphic, and we've assumed that it has some automorphic lift RL of pi. And what we want to do is construct two extra ordinary lifts, R prime and R double prime, and we're going to want to apply a bunch of modularity lifting theorems to eventually allow us to deduce that R is automorphic. So we're going to start over here, and we're going to try and construct R prime so that we can apply theorem 3 to it. So what we're going to have to construct R prime, R double prime, so that locally away from L, it's lying on the same component as RL of pi. And then we're going to have some other ordinary lift, R prime, that, again, we're going to want, if we knew, so it's going to be constructed so that if we knew this guy was automorphic, R prime, we could then apply theorem 3 over here. So in other words, R prime is lying on the same component as R locally away from L. And then how are we going to deduce that this is automorphic? Well, we're going to use an ordinary lifting theorem. And that didn't make any condition on what was happening away from L. Okay, so just to be precise, what we need is R prime and R double prime are ordinary above L with distinct Hodge-Tate numbers. Now, we need to ensure that the Hodge-Tate weights of these lifts and R double prime tensor RL of pi have distinct Hodge-Tate weights. So that we can apply Theorem 3. And lastly, we want that R restricted to GFE connects to R prime restricted to GFE at V not dividing L, and R double prime restricted to GFE connects to RL pi restricted to GFE, again a V not dividing L. And then again a remark. I said the ordinary lifting theorem has no, maybe I made this remark earlier actually, sorry. No connects to condition at V not dividing L. So if we can do this, we're done. Okay, because we just apply the theorems in the order written down there, and so the only thing that remains is to explain how to construct these. So we're going to construct them using the method of Carré and Vandenberger. So how does this go? So let's construct. So let's do it for R prime. Okay, so now we're just going to go back to some of the notation we had before when we looked at deformation theory. So S is going to be the set of primes V dividing L, union all primes at which R is ramified. And again, I'm going to assume each place in S is split over F plus. And what we're essentially going to do is just write down a deformation. We're going to write down a deformation problem that parameterizes lifts of the form we're looking for. So for V and S, V not dividing L. So I mean, maybe I should really only be working with half of the places in S when I'm doing the deformation theory. But since we've seen that sort of thing before, I'm just going to not be too precise about it. I'm going to let CV be an irreducible component of the lifting ring, of the local lifting ring, and this component has to contain R restricted to GFE. And then I'm going to let RV be the ring that I denoted R box sub CV. So this is the this is a quotient of the lifting ring, which is reduced in L torsion free, and it's supported on this chosen irreducible component that we've singled out. And now what are we going to do at places dividing L? For V dividing L, so choose appropriate Hodge-Tate numbers for R prime. So essentially we just have to make sure that R tensor R prime will have distinct Hodge-Tate numbers. So we have complete freedom in what we essentially, well, we have a lot of freedom in what Hodge-Tate numbers we choose, and we can certainly guarantee this. And then we're going to let RV be the following ring. So we're going to take the universal lifting ring, and we're going to look at crystalline ordinary lifts with these Hodge-Tate numbers. And again, we may assume this ring is non-zero. By making a finite base change if we need to.
This is an important point that you're passing over, because somehow by making this finite base change, you're eliminating the restriction on L relative to the Hodge-Tate.
Yeah, I mean, I guess we could just start with something that looks irreducible locally, residually irreducible. So we make a base change so it could be maybe the case that over the base field, there's no hope for ordinary lifts to exist.
Right.
Yeah.
I mean, this approach just repeats so that people are
Yeah.
already doing that.
Yeah. Probably shouldn't have glossed over it so quickly.
Can you remind us, by definition, RV is in characteristic 0 here?
Yeah.
Yeah.
Yeah. So anything in characteristic L should have a bar on top of it. So maybe just to say, how would you make a base change to show that this ring is non-zero? Well, just first of all, make a base change so that the residual representation is trivial. Now join Lth roots of unity, and then just take a sort of direct sum of powers of the cyclotomic characters, something like that. Where I should go next. Maybe here. And now so we have a deformation problem. So to use the same notation as I had before, we have a bunch of data. We've got our CM extension. We have some choice of coefficients. We've got R bar. We've got our multiplier character. We've got the ramified places at which we're allowing ramification. And then we have these chosen quotients of the lifting ring at these places. And we have a corresponding deformation ring. So this this universal deformation ring, just to say it in words, parameterizes deformations which are unramified outside S, have fixed multiplier character, and locally factor through these chosen quotients of the lifting ring at the places in S. So now it's enough to show that there exists characteristic 0 lifts of this type, script S, and to achieve that, it's just enough to show that the generic fiber of this lifting ring is non-zero. And so what is the method of Karajan-Vandenberg for showing this? Well, it's to, first of all, use a bound on the Krull dimension. So we know from a Galois cohomology calculation that the Krull dimension of this ring, and this is something I mentioned, I think, in one of the first couple of talks, that this ring will have Krull dimension at least 1. And now we want to somehow show that So it's enough to show that the ring is finite over ZL. So if you have a ring which is a finite ZL module and has curl dimension at least 1, then its generic fiber can't be 0. And how are we going to do this? Well, we're going to apply theorem B from last time. So that says that there exists f prime over f Cm, Galois, and a pi chi over f prime, such that r bar restricted to gf prime is r bar, rl bar pi, and pi is ordinary. And now so now we had the ordinary lifting theorem came from an R equals T theorem. So it was a result of the following form where we had a R equals T, but it was an R reduced equals T, and this is some ordinary Hecke algebra, and in fact we can take it to be a fixed weight, Hecke algebra of fixed weight. So in particular this thing is a finite ZL module, and this was some deformation ring for ordinary lifts which are ordinary above L. And if you remember that we also, at the places away from L, this was parametrizing semi-stable lifts, or semi-stable at B not dividing L, and that just means we're looking at lifts where inertia acted unipotently. And this takes place over some solvable extension of F plus. And then to finish off, we make another base change, so extend L to ensure that, let me just say, for all W dividing V and S, W in place of L, and W not dividing L, R restricted to GLW is semi-stable. And let me say, this implies that if I take anything on this chosen component, let me just write this somewhat imprecisely. So if I take anything on this chosen component of the lifting ring and restrict it to a decomposition group W as above, then whatever you get will have unipotent ramification. And what this implies is that that we get a map from this ring I've just called R to the one I constructed, and this is just coming from restriction to GL, and then the point is that this map is finite. And since we know that R red is a finite ZL module, because it's isomorphic to Heck algebra, which is a finite ZL module by definition, we get that R is a finite ZL module and hence so is the ring we started with, and we're done at this point.
I'm confused how R red is finite. Why is it R is finite?
That's what was the argument for that? So, I mean, it's like a one-line argument. I'm just trying to remember what it is.
It's not a priori true in commutative algebra, right? You could have a characteristic component characteristic P.
Well, probably like this is Noetherian. It probably uses Noetherian, and
I'm just worried like ZP double brackets X modulo PX.
Reduce means modulo the
nil.
arithmetic or not.
Oh, no, not R1 on P. This is R red. Okay.
So we're just killing the nilpotents.
Yeah, sorry, I was confusing.
Yeah.
The generic
I just can't think of my feet with the actual. I mean.
No, what I was thinking was.
Uh-huh.
Was the generic five.
Okay. Okay.
Right, because this is actually a minimal lifting there.
This was a non-minimal. This was somehow the argument of Taylor that I explained last time, where these unipotent lifting.
Okay,
Yeah.
right.
But you got it. You got all components were in the support.
That's
Yeah,
all
full.
components rather than just a specific.
Exactly.
Okay, so-
Exactly.
okay, good.
Yeah. So you really need that.
Yeah.
All right. So I guess sorry for going over.